Fellow students, good morning. Welcome. Today is the 21st of April 2020. We'll be concluding with chemical energetics. I just want to give a summary on all what we have been doing for the past few days. Chemical energetics has to do with energy that is being absorbed in bond breaking and reactants, and the energy that has to do with when energy is released to the surrounding when bonds are formed in products. Initially, before the starting of this topic, we mentioned that fuels, these are substances that release energy when they are burnt. When they are burnt, energy is being released. Any substance that releases energy when it is being burnt is fuel. We gave an example of fossil fuel. We gave an example of hydrogen. We gave an example of nuclear energy, like uranium. Fossil fuel are the common example that we have been using. We use an example of methane. Another example is ethanol. Another example is hydrogen. Hydrogen, when it burns in air, it will release energy, but the byproduct is water. It does not release carbon dioxide, which is a greenhouse gas. And for that reason, nitrogen will not cause global warming. And nuclear energy, for example, uranium, which is widely used today, is another source of energy. It does not release carbon dioxide. For that reason, it does not cause global warming. And for that reason, it is a better alternative to fossil fuels. Further, to go in to discuss about, we went further to discuss about exothermic and endothermic reactions. About exothermic reactions, I told you exothermic reactions are reactions. Exothermic reactions are reactions. Exothermic reactions are reactions that energy is released to the surrounding when bonds are being formed. Endothermic reactions are reactions where energy is absorbed from the surrounding in breaking bonds, reactants. And then we went further. We said the energy change for an exothermic reaction is always negative. It has a negative value. Then the energy change for an endothermic reaction is always positive. That is, it has a positive value. In exothermic reaction, there is bond breaking. In exothermic reaction, there's bond formation. And in endothermic reaction, there is bond breaking. We went further to discuss how in activation energy, how you can draw an energy profile diagram for an exothermic reaction. This is an exothermic reaction. This is an energy profile diagram, reaction of progress on the x-axis, the energy in kilojoule per mole. These are the reactants and these are the products. If you look at it, you will see that the activation energy for an activation energy, that is the minimum amount of energy for a reaction to occur, for an exothermic reaction is small. It has a lower activation energy compared to the activation energy used in endothermic reaction. Let's go to an endothermic reaction. In an endothermic reaction like this one, look at the activation energy there. Reaction, the activation, it has a higher activation energy. It has a higher activation energy. Then we went further on how to calculate the energy profile. I mean the energy bond diagram. In calculating the energy bond energy calculations. For bond energy calculations, once more, I said bond energy is the amount of energy that is needed to break 1 mole of a covalent bond in a gaseous molecule. That one is in reactants. If you are also asked to define bond energy in terms of products, you will say the bond energy is the amount of energy that is released when 1 mole of a covalent bond is formed in gaseous molecule in a product. Remember, all these are measured in kilojoules per mole. We went further to solve an example. Here was the first example that we solved. We said calculate the energy change for the reaction between hydrogen and the chlorine. The first thing I said that you have to write your equation, a balanced chemical. The second thing is you have to write the bonds out. And the third thing is you use the formula. The formula says the energy taken in to break bonds in reactants minus the energy released when bonds are formed. When you do this, you substitute the data here, you have that the total amount of energy that is required to break bonds in reactant is 677. And the total amount of energy that is required to released when bonds are formed in products is 862. And the energy change between the reactants and the products would definitely be minus 185 kilojoule per mole. And we can conclude that this reaction is an exothermic reaction because the energy change for the reaction is negative. It has a negative value. We went further to calculate more. We went further for more examples, like this one here, like the one here. Let me just show you for example this one. We went further to calculate the energy change for a reaction like this one. We said, calculate the energy change when 2 moles of hydrogen molecule react with 1 mole of oxygen to form 2 moles of water molecule. Use the data that has been given to calculate the energy change. Part B of this very question says, use your values of total energy taken in, that is in breaking the bonds, total energy released, that is when bonds are formed, and the enthalpy change value to draw and label a good energy level diagram for the reaction. I told you in our previous example, I said the first step you do is you write a balanced equation. And if we write that, we have this. The second step is when you draw out the bonds. When you draw the bonds in the HH and the OO and in water, you will see them out. Then after you draw the bonds, you have to calculate how many of the HH bonds are there, and the OH bonds are there, and the OO bonds are there. And if we do the calculation, we'll have that is 2 times HH bond, it is 1 times OO bond, and it is 4 times the OH bond. When we have this, the third thing is we have to use the data that has been given and substitute to see if we can get our answers. When we substitute the data, we will see that in the product section, that's the HN and the OO bonds, is 2 times 435, which is 435 is for the HH bonds. Then it is 1 times 498, which is for the OO bond. And the total energy that is required to break the bonds in reactant is 1368. If we go to the products, it is 4 times the OO bond and the OH bond. And the OH bond is what? It is 464. When we do that, the total energy that is used in breaking that is the total energy that is released when bonds are formed is 4 times 468, which will be 1856. Step number 4 should be we use our formula. We have to use our formula. The formula says energy taken in breaking bonds in reactants minus energy that is being released when bonds are being formed. In doing this, we will say the total energy that is taken in breaking bonds in reactant is 1,364 kilojoule per mole, minus the total energy that is released when bonds are formed, which is 1,856 kilojoule per mole. And our energy change for the reaction will be negative 488 kilojoule per mole. Therefore, our conclusion should be the reaction is exothermic, because in our previous example we said if any reaction energy change for any reaction that is negative, the energy change for any reaction that is negative is exothermic. For any reaction, if the energy change is negative, we call that reaction an exothermic reaction. Therefore, this reaction is an exothermic reaction. In the part B of this question, you were told use this. You were told to use this and draw an energy level for the reaction. And this is the reaction. This is the energy level diagram for the reaction. This is the energy level diagram for the reaction. If we use the total energy, we have to draw the y-axis and put it as energy in kilojoule per mole. You have to draw the x-axis and put it as reaction progress. Since it was an exothermic reaction, the thing we have to start it from the reactant here, and where the products are formed should be below. Then we have to label it rightly and put the reactants here and put the products here. On the reactant, we have to use the total energy that was taken in breaking the reactants, which is 1368 kilojoule per mole. On the product side, we have to label it by putting the total energy that was released when a molecule of water, when 2 moles of water were formed. We say it is 1856. Then the difference between the energy of the reactant and the energy of the product is the energy change. The energy change, we have to label it, and in labeling it, we have to put delta H is equal to -488. Then the last thing we should do in labeling our diagram very well will be to indicate the activation energy EA for the reaction. When we do all this, you have your answer right. Conclusively, I will say, you know, anything that can burn releasing energy. We give example of fuels to be like hydrogen. We give example of fuel to be like uranium that is used for nuclear energy. We also talk of fossil fuel like something like ethanol. We also talk of other organic compounds. We went further about bond breaking, about isothermic reaction and endothermic reaction, how you can differentiate exothermic reaction and endothermic reaction in terms of bond breaking, and bond formation, and in terms of their value of the energy changes. Then we went further how you can use this in calculating the energy change by calculating the total energy absorbed in breaking bonds in the reactant, and by calculating the total energy that is being released in bond formation. And how you can use this and draw a good energy level diagram for a reaction. You can now determine whether the reaction is an exothermic or an endothermic reaction based on the energy change of that reaction. When you do this, then you are sure of having a good grade. Thank you very much for listening. Bye-bye.